Hello, Slava.
Hi, Stefan.
From EHS. You did graduate from Princeton in 2002, and then, according to what I found, were assistant professor at Scuola Normale in Pisa from 2007 to 2009, followed by appointment in Paris 6, being a staff member at CERN, an ENS chair, and finally a permanent professor at EHS since 3 years ago. You've received a number of prizes, among which are the Grand Prix Merger Bourdais, sorry for my bad pronunciation, and the New Horizon Prize. And we're very curious about CFT and its connection to boiling water.
Okay, thank you very much, Stefan. And I should also thank Antti for originally inviting me to give this talk and for suggesting the subject, because he knew that of our ongoing project. So this is going to be based on an ongoing work with Petr Kravchuk, who is a postdoc at the Institute in Princeton, and my PhD student Jiaxin Qiao. So this is not my usual audience, so it's a bit challenging. You should feel free to interrupt me if I'm going too slow or too fast. So there's going to be some things that you know much better than me, other things probably more unusual for you. It's going to be a talk about axioms in quantum field theory. In particular, I will discuss the relations between three families of axioms which all deal with correlation functions in infinite flat space, namely Wightman axioms, Osterwalder-Schrader axioms, and Euclidean CFT axioms. So I will not discuss today other axiomatic systems which deal with other observables, other objects like Kastler or Siegel axioms, although those things are also interesting. But why should we care about axioms? So there are two reasons to care about axioms. One, some people are interested in constructing quantum field theories, and there are many ways and many tools to do this. You can do a Hamiltonian approach or path integral approach or stochastic PD approach. But in the end of the day, you have to verify that your construction satisfies quantum field theory axioms. So it's a sort of measure of success. And for example, the three-dimensional 5⁴ theory has been constructed according to this criterion, and the four-dimensional Young-Mills theory not yet constructed. The second reason to be interested in axioms is that it's really cool to start from axioms and try to derive some concrete predictions, hopefully experimentally verifiable predictions. And one example of such approach has been the S-matrix bootstrap program, which had initially some success in the 60s and early 70s. Then it also had some success about the integrable two-dimensional quantum field theories in the work of Zamolodchikov and others. And lately has been interestingly some revival of this S-matrix bootstrap program, which goes beyond integrability and again tries to look at massive quantum field theories in 3 dimensions and higher. But I think it's fair to say that so far it has been pretty hard to make sharp predictions for massive quantum field theories in 3 and higher dimensions using just some axiomatic rules of quantum field theory. On the other hand, and this is more recent, so there was some progress in massless, more exactly in conformal quantum field theories. where actually using axiomatic approach, some experimentally verifiable predictions have been made. So to give just a couple of examples, it is conjectured that there are some unitary three-dimensional conformal field theories which describe the second order phase transition in ON models, in lattice ON models, such as three-dimensional Ising model, O2 model, and other ON models. And so if you take these conformal field theories, if you assume they exist, and if you impose on them this Euclidean CFT axioms that I will talk about, then you can actually constrain the correlation functions of these conformal field theories pretty well, to the extent that you can get some results about critical exponents such as eta and nu, but you can actually get much more information about these conformal field theories. But since critical exponents is something that can be measured, you see that that you get pretty interesting results with many digits. So so I don't want to talk today about how those results are obtained, because this would require a lot of time. But this is just as an example that that Euclidean conformal field theory is a pretty powerful framework to constrain at least Euclidean correlators of the theory. And so it is then natural to ask that perhaps it can also capture other aspects of the theory, and, for example, Lorentzian physics. So it's a natural question. And actually, interestingly, if you look at the history of the subject, if you look at the classic conformal field theory papers, which were published in the 70s, so there was some pretty impressive work by Luscher and Mach and by Mach. And in those papers, in those communications of mathematical physics papers, they actually imposed some mixed assumptions. So their assumptions were a mix of Lorentzian and Euclidean assumptions. For example, they assumed Wightman axioms from the start, and on top of that, they also assumed Euclidean conformal invariance and things like that. So that was maybe looked natural in the 70s, because in the 70s, most people were really coming from the direction of particle physics. But then after this initial period, for a very long time, most conformal field theory research was actually motivated by statistical physics. It was Euclidean, mostly purely Euclidean considerations. However, recently, there was a sort of an interesting development, that there was a revival of Lorentzian considerations, which actually, not just Lorentzian for the sake of Lorentzian, but they have even some unexpected Euclidean consequences. So I just want to give you one example. There is such a thing that has been a lot discussed lately, which is called average null energy condition. So it's a condition on the stress tensor of conformal field theory. So if you integrate it over some null direction, then this is supposed to be a positive operator. So its expectation value in any state has to be non-negative. So this is a really an inherently Lorentzian condition. In order to formulate it, you have to have access to the theory in the Lorentzian signature. But interestingly, this Lorentzian condition, it gives rise to some constraints on purely Euclidean parameters of the theory. For example, you can extract from it some constraints on the three-point function of the stress tensor of the theory, which are meaningful even in Euclidean signature for Euclidean statistical physicist, conformal field theorist. And moreover, these constraints that you get this way, they do not, to this day, have any purely Euclidean derivation. So this is really this kind of curious. This is unexpected. And so this raises the question, is Lorentzian consistency of conformal field theory, is this really an extra assumption, or this is actually something which is already contained in Euclidean CFT axioms? And I think it's fair to say that most people, most researchers nowadays believe that it's not an extra assumption, that actually it is somehow automatically, Euclidean unitary CFT is automatically well-defined in Lorentzian. For example, it should satisfy Wightman axioms automatically as a consequence of Euclidean CFT axioms. So this is a conjecture, and today I will present some results which go towards showing this conjecture. We cannot yet fully show it, but we can show some things. Would be totally happy to take questions. So if there is anything which comes up, please feel free to interrupt.
Yeah, there seems to be a question indeed. Jan?
Yeah. Hello. I have not fully understood. So you said you impose the average null energy condition, and then you can draw in consequences for the Euclidean theory. But as you said, this condition is only meaningful in a Lorentzian setting. So how does this relation work to go from the Lorentzian to the Euclidean setting?
Well, from the Lorentzian to Euclidean, it's not so surprising because, of course, you can take a Lorentzian. The question is, suppose you are a statistical physicist and you study, say, the Ising model CFT, and you derive some constraints on the Ising model CFT. And then somebody comes and says, well, I will assume in addition that this Ising model CFT can be analytically continued to the Lorentzian signature and satisfy some constraints out there in the Lorentzian signature, for example, Wightman axioms. And from this, I will derive more constraints. This is the claim. Now, okay, this is like magic. So the claim, now the question becomes, by assuming the Wightman axioms, did this person really bring in additional constraints, or was it just some very non-trivial repackaging of constraints that already existed in Euclidean, but somehow were not visible there? So I think the conjecture is that actually it is repackaging. So these constraints are already somehow secretly contained in Euclidean physics, but they just become much more visible, much more natural when you consider these Lorentzian analytic continuations. So that's.
Have a question.
Yeah. Hi, Madam.
Hi, Slava. I don't understand your conjecture. It seems that it should follow just from Osterwalder-Schrader theorem, because it seems you're assuming OS axioms, or you're not.
No, I'm not assuming OS axioms. I'm assuming Euclidean CFT. Later on, we will see why this is non-trivial.
Okay.
Okay, so we can go ahead. But in fact, I have to start, since this problem has been famously considered problem of constructing Lorentzian from Euclidean by Osterwalder-Schrader. I have to start with a refresher of what has been actually done, and I'll try to not be too pedantic about this, because this kind of this is bread and butter of quantum field theory. So most people have some idea about what they did. So in this Osterwalder-Schrader framework, we consider Schwinger functions. So these are correlation functions of fields in local fields in Euclidean space, which are translation and rotation invariant. So every field transforms in some irreducible SOD representation. Let me just limit to bosons for simplicity. And these correlation functions, they are defined at non-coincident points. And I'm twisting the story a little bit, but it's basically we can assume that they are real analytic and have at most power-like singularities at the coincident points. And the important thing here, the non-trivial thing here are these hermeticity and positivity axioms, which are defined with the help of this reflection operation, which takes a d-dimensional vector and it flips the first component, x0 to minus x0. So this is the reflected position x theta. And then, okay, I'm only going to limit to scalar fields for simplicity for interest of time. These hermeticity and positivity axioms, they can be stated as follows. So hermeticity axiom just says that if you take a Schwinger function and its complex conjugate, then it's equal to the Schwinger function at the reflected positions, xn theta, x1 theta. And the fact that the same fields phi k appear in the right-hand side as in the left-hand side, this means that I'm dealing with the Hermitian basis of fields. And the positivity axiom, okay, I'll be a little bit intuitive here, not super rigorous, but roughly what you have to do, you have to consider states, and states are formal halves of correlation functions. So the states are specified by a bunch of operators inserted at some positive times and ordered times. So the times are x10, xn0 are ordered, increasing. And so if you take some other state of this form, psi tilde, which is where I insert some other operators, chi1, chi-m, then the inner product of the states is defined as a correlation function, m plus n correlation function, where I'm inserting the chi fields at the inverted positions, at the reflected positions. So this is the inner product, and I extend this inner product to finite linear combinations of states. And then the axiom says that such an inner product has to be positive semi-definite. So this is all very classic if I am cutting some corners in the interest of time, but I hope it's all very familiar. And when Osterwalder-Schrader considered the problem of deriving Wightman axioms from OS axioms, then this problem was split roughly into two stages. So the first stage is that you have to analytically continue Schwinger functions to complex times. So you take times xk0, and they have to be, you analytically continue them to complex values epsilon k plus itk, where the real parts have to be ordered, and the imaginary parts can be arbitrary. Tk can be arbitrary. So first you construct such analytic continuation, and then as a second step, you take a limit where all the real parts go to 0. So this limit now depends on TKs, which become your Minkowski times, and on the special parts of the vectors, xk vector. And of course, you have to show that this limit exists and that it satisfies Wightman axioms. This is the hard part. And okay, Wightman axioms, I'm also not going to go through the full list. It's so I mean here by Wightman axioms properties of Wightman functions, so properties of expectation values of fields. And one thing that I want to emphasize here only is that the Wightman axioms, they have to be tempered distributions. The Wightman functions have to be tempered distributions. So this is very important for various reasons, but one clear reason, for example, is that without having tempered distributions, you cannot even properly formulate positivity for Wightman functions, because unlike in the Osterwalder-Schrader axioms, when you take the complex conjugate state. When you take the conjugate state, you reflect the positions of the operators. And so all operators are at non-coincident points, and the inner product is a finite quantity. But for Wightman functions, when you take conjugate, then the position does not change. And so you have to integrate fields across coincident positions. And so unless you know what happens at coincident positions, you cannot even properly formulate positivity. So you do have to show that your functions, Wightman functions, are distributions, and tempered distributions is a very natural class of distributions, which allows you to formulate both the commutativity condition and the spectral condition in a natural way. This is the classic framework. So there are these two steps, 1 plus 2, but actually there is a classic way to show temperedness, given that you already constructed analytic continuation. So this is the way which is used basically by everyone. And the trick is to show that when you consider this analytic continuation of Schwinger functions, that this analytic continuation grows as the real parts go to 0, not faster than a power law. So it has to be some power in 1 over the minimal difference of Euclidean of the real parts of the complexified times. So if you can show this, then some not very complicated theorems of several complex variables tell you that the limit exists. It is a tempered distribution. Actually, this power n is going to be to determine the regularity of the limiting distribution. And actually, all the other Wightman axioms follow basically for free. I mean, you have to work a little bit, but it just falls at you for almost for free. So this power law bound is really crucial to show temperedness of Wightman functions. So this is just a reminder. The history of this theorem has been somewhat complicated, because the first proof of that Osterwalder-Schrader axioms imply Wightman axioms, it had an error. And then there was a very nice paper of Glaser from 1974, who pointed out that unless you make some extra assumptions, the Osterwalder-Schrader axioms, they allow you to analytically continue the Schwinger functions all the way to Minkowski space. But let's say an epsilon away from Minkowski space, but you do not know, you cannot establish the temperedness bound, and so without some extra assumptions, and so you cannot show that the Wightman functions actually are tempered distributions. And so what has happened next is that Osterwalder-Schrader, they published a second paper where they fixed the error. They used this construction of Glaser plus an extra assumption, which I will talk about later. And this, now they derived the Wightman axioms. So that's how it all happened. And so, so what is this construction that they used, and what is this extra assumption? Let me just briefly say a few words about it. So as we have seen, the Schwinger function can be represented as an inner product of two states. So I can take an n plus m Schwinger function and present it as a product of state depending on n fields and another state depending on m fields. So because of this formula, analytically continuing Schwinger functions becomes basically equivalent to analytically continuous states. So there are two methods which can allow you to extend the region of holomorphy of states of Schwinger functions. So the first method, you have to use both of these methods. So the first method is that you can take any state and you can act on it with a Hamiltonian semigroup. You can construct a Hamiltonian in this OS framework. And if the real part of the parameter of the semigroup is positive and the imaginary part can be anything you want, then this gives you again a new state of bounded norm. And so using this trick, you can fully extend a range of complex times for just one variable, but only one variable at a time. So you have to use a second method, which is the method of envelope of holomorphy. So you apply the first method on different variables, and then you use the envelope of holomorphy arguments, and you have to do it in alternation. You have to alternate these two methods, and gradually you can build up phase of all complexified times all the way to pi over 2. But you actually have to do this alternation of steps infinitely many times in order to reach pi over 2. So it's kind of a recursive construction. So, just to give for one example, so suppose you study analytic continuation of an 8-point function. So you represent it as an inner product of psi4, but you can equivalently write it as psi6, psi2, or psi2, psi6. In both of these cases, you can insert the Hamiltonian semigroup in the middle. So you obtain two different analytic extensions. Then you use some convexity arguments to argue that you can get back to a diagonal inner product of some other state psi4 tilde, psi4 tilde, which you would not get just by Hamiltonian semigroup. And so you keep going. And so you see that here I had to introduce this state. So I was interested in the state depending on 4 fields, psi4, but I had to introduce the state which also depended on 6 fields. And actually, this is the feature of this argument is such that it's, in order to continue, say, psi4, it will necessarily require to continue psi6, psi8, and all the other states with arbitrary number of fields. So it's a sort of all or nothing argument. And moreover, as I said, you don't just have to analytically continue, you also have to keep track of the growth of the analytically continued correlators. And this can be done. So you can actually keep track of the growth by applying repeatedly Cauchy-Schwarz inequality. And you can reduce everything to Euclidean correlators. But what will happen is that these Euclidean correlators will be of arbitrarily high order, because you will need infinitely many steps. And so to deal with this, Osterwalder-Schrader introduced this growth condition. So they said that the Schwinger function of order n integrated against some test function, this pairing should grow not faster than some Schwarz semi-norm of the test function times some power of the factorial of n. So it's just some condition that they cooked up. And well, that's the condition we live with ever since, because it's kind of the state of the art. So this finishes my review of the Osterwalder-Schrader Glaser construction. And now I'm going to go to the CFT story, but this review is going to be not totally useless, because we will see that the CFT story is in some aspects quite similar to this Osterwalder-Schrader construction. In other aspects is different, so it will be interesting to compare. But maybe there are some questions about what I just reviewed, or some remarks, because I'm basically preaching to people who know this more than me. So I hope I didn't get anything wrong. Okay, so let us then go to the CFT story. And let me now finally introduce this Euclidean CFT axioms. In conformal field theory, and I'm only going to consider conformal field theory in flat space, in infinite flat space, we are dealing with correlation functions of fields. And these fields, they are characterized by an SOD irreducible representation, just like an Osterwalder-Schrader axioms. But in addition, they are characterized by a real positive parameter, which is called scaling dimension. And this scaling dimension, it determines how the fields transform under rigid dilatations. So the fields just rescale by the factor lambda to the delta I. But of course, in conformal field theory, we don't just have rigid rotations and dilatations, but we also have, in general, we impose invariance under all global orientation preserving conformal transformations. So these are transformations of f of Euclidean space to itself. Actually, strictly speaking, I should be talking about transformations acting on the Riemann sphere, but let me gloss this over. And these transformations, they form a group, SOD plus 1, 1, which includes all the rigid transformations as subgroups. And actually, there is no, so once you fix the transformations of fields under SOD and under the dilatations, then everything else follows, because any conformal transformation, it is characterized by some local dilatation factor lambda of x and some local rotation factor, which also may depend on x, which is a matrix which depends on x. And so fields under conformal transformation, they transform by some matrices m alpha beta of x, which depend on lambda of x and on the rotation matrix R of x. And this dependence, I'm not going to write this down, but it is an induced representation. So it is uniquely fixed by consistency with rigid SOD times dilatation. So that's the only thing. So the theory is completely fixed by these requirements. So this is the basic framework. And now we have to discuss the less trivial axioms, which are the positivity and the OPE. So the positivity axiom is kind of similar to the Osterwalder-Schrader positivity, except that it is imposed only on 2-point functions and 3-point functions of the theory. So here I'm going to explain this for simplicity just for scalar fields. So there are 3 parts to the positivity axiom. The first part says that the 2-point functions have to be diagonal. So the field has a 2-point function only with itself. The second part of the positivity axiom says that if you take some field and you take the derivatives of this field, and then you form 2-point functions of these derivatives. but you form them in the reflection positive. You form them in kind of reflection symmetric way. So you put a certain derivative of a field, and the second field is going to be a field, the same field put at a reflected position, x theta, so it's the same reflection as for Osterwalder-Schrader, and also reflect the derivatives. So every time I take a derivative with respect to x0, there is a -1 factor. So I take this infinite matrix of derivatives, of two-point functions of derivatives, and the condition says that this matrix has to be positive semi-definite. And actually, this looks like a fancy condition, but you can show that for scalar fields, it just reduces to the requirement that the scaling dimension has to be larger than or equal d/2 - 1. And there is a similar condition for all other representations in which the fields may transform. And for all of these representations, there's always these conditions, they always are equivalent to saying that the dimension of the field has to be larger than or equal than some bound, which however depends on the representation. These are the so-called unitarity bounds on the dimensions of fields. And then finally, there is a third part to the positivity, which is imposed on the three-point functions, and it says that the three-point functions must be real. Well, actually, in conformal field theories, the three-point functions are completely fixed by conformal invariance. Their functional form is completely fixed by conformal invariance. For example, for scalar fields, it's just some rational function of the distances x1 minus x2 to some power, x1 minus x3 to some power, x2 minus x3 to some power. And these powers are fixed in terms of the scaling dimensions of the three fields. And so what has to be real is just the prefactor. So there is some number which is the only parameter not fixed completely by conformal invariance, and this parameter has to be a real number. Any questions about positivity?
Yes. So here the fields themselves do not have to be real.
The fields. So you see, fields in conformal field theory, they're just labels. They're just letters. They are not. So to say that the field is real means that the correlation functions have to satisfy some reality properties. So in other words, what I'm saying here is that by formulating these reality conditions on the two-point functions, on the three-point functions, I'm basically saying what it means for a field of conformal field theory to be real. Because it's very different from the path integral approach, because in the path integral approach, we have a certain measure, and so we know our field is a field. It has some life as a random distribution, and then it makes sense to say if it's a real or not real. But
if I think of something like an order-disorder variable.
No, it's not a variable. It's just a label. It's just a letter.
Yeah, but I want to understand how would this description capture what we concretely mean by order-disorder variable in the standard representation of the, say, two-dimensional Ising model.
It does not capture those fields.
Okay.
So
it captures things like spin variable, spin fields, or disorder fields, but not their combination.
But it doesn't capture those ordered disorder.
Thank you.
Slava, is there an analog of these conditions for the Virasoro invariance instead of the different definitions of primary versus quasi-primary?
Yeah, there are some completely analogous conditions also for two-dimensional conformal field theories, where you, for example, this condition P2, the usual unitarity condition of two-dimensional CFTs, where you consider descendants, not just derivatives, but there are some other types of descendants. But in the end, there's always some big matrix that you form, and that matrix has to be positive semi-definite.
So this could a priori give a proof, like for example, for Ising, the correlations are completely explicit with that square root sum over charge distributions and all that. But I haven't seen a proof of Osterwalder-Schrader positivity using just that explicit, without using a big detour by like results of obtaining from scaling limits of a critical lattice model and things like that.
Yeah, yeah, to me, it seems like it's really obvious from this framework, this sort of questions are really easy to answer. But maybe you should talk about that particular example later, because, yeah. So the last axiom is the operator product expansion axiom. So it says that any correlation function of the theory, it can be computed via OPE. So I can take, say, two fields, phi1, phi2, the first two fields, and I can replace them by a series. And some parts of the series, like the coefficients f1 to k, are the same coefficients which appear in the 3-point functions. And here there are scaling dimensions, delta 1, delta 2, delta k. But then there is a part of the series which is completely fixed by conformal invariance. And so this series, it reduces n-point functions to n-1 point functions. And the axiom says that this series is convergent, provided that the 2 points that you are doing OP, x2 and x1, the point x2 is the closest point to x1 from all the other points. So then the series is a convergent series. You can try to give some motivations for this axiom, but let's not go into motivations. So it is from these axioms that all those results about critical exponents have been obtained. And there is some story about, given that any CFT satisfies these axioms, how do we actually distinguish one CFT from the other? Because we would like to compute critical exponents for Ising model, not from some other model, and so on. But okay, there is some story there, but in interest of time, I have to skip this. I'm sorry. And so I'm going to now consider my problem is how to get Wightman axioms from Euclidean CFT axioms. And a priori, there are two strategies. And one strategy is to try to go through Osterwalder-Schrader. So then I take Euclidean CFT. First, I derive Osterwalder-Schrader, and this is really easy. This is almost obvious that Euclidean CFT applies Osterwalder-Schrader. And then I try to use the fact that Osterwalder-Schrader applies Wightman. But here I'm blocked because I see no way to verify the growth condition on n-point functions of arbitrary order using just Euclidean CFT axioms. I don't know what it means in terms of Euclidean CFT axioms. Just some extra condition that I can assume, but yeah, but I don't want to. I don't know what this means. So I'm not going to follow this route. I'm going to take a different strategy. I'm going to use OPE. Because you see, operator product expansion, it gives an expression for Euclidean correlation functions, kind of recursive expression, where coefficients are just some explicit functions of x, some powers of x. So these functions can be taken and they can be analytically continued to complexified times. And now, of course, I have to, there's no guarantee that it's going to work, because I have to try to see if I can go all the way to Minkowski without, keeping convergence of the series under control. And also I have to see if I can control growth of this analytic continuation as I approach Minkowski. And so today I'm going to explain how this works in the 4-point function case. So the 4-point function case is actually the first non-trivial case for conformal field theories, because 2-point functions and 3-point functions, they're given by some explicit formulas, and just from these formulas you can get all the needed properties, analytic continuation, Wightman, axioms, whatever you want. So the 4-point function is the first non-trivial case, and also it's kind of the case most important for applications. So for example, all these results for critical exponents, they are obtained using 4-point functions. So let me consider a 4-point function for simplicity, identical scalar fields. And in the conformal field theory, this 4-point function is given, just imposing constraints of conformal invariance, is given by some function of the distances which depend on the dimension of the field, times g of uv. This is the usual form, and g of uv is a real analytic function of conformal invariant cross ratios. So from 4 points I form conformal invariant cross ratios. So u, I wrote this well-known formula here, and v is just obtained from u by exchanging x1 and x3. And g is some function of these cross ratios. But given that we have the OPE, we can actually express this function of the cross ratios in terms of parameters of our theory of scaling dimensions and of OPE coefficients.
Is there a typo in the equation with x1 being x3?
X1 being
The second x1 in the numerator.
X1 minus x3, x1 minus... No, there's no typo. V is equal to R.
Yeah, numerator of u.
Yeah.
Yeah, I'm sorry. Yeah, you're totally right.
Just to be sure.
Thank you. It's well known, but we have to still write it correctly. So, so in other words, this function GV, it has some interesting power series expansions. You can write down some interesting power series expansions for it. And so we have to see what is the best power series expansion to use in order to perform this analytic continuation to Lorentzian. And we basically found one expansion which is magical, so it works. So let me describe this expansion, and okay, one can try to motivate why this is the right expansion, but I'm afraid that it's of a very acquired taste, so kind of appreciation requires some prior knowledge of CFTs. So, but you know, let me just like present it to you as a machine. So the point is to choose the right coordinates. So we can, I told you that there are these two cross ratios u and v. But from these coordinates u and v, I can pass to two complex coordinates z and z bar by these formulas: u equals z bar, v equals y minus z, y minus z bar. This is pretty standard. But then I'll do something less standard. I pass from variable z to this other variable rho by this formula. Now, this formula, analogously for rho bar, this formula may look somewhat mysterious, but actually it has a it has a simple geometric meaning. If I have 4 points in the d-dimensional space, then I can always find a conformal transformation which maps these 4 points to a plane. And moreover, I can arrange that the images of these 4 points in the plane, they are symmetrically distributed with respect to the origin of the plane. So I can map 2 points to 1 and -1 in this plane. And also I can map 2 other points so that they're symmetric around the origin. And so there is a certain distance r and there is a certain angle phi. And in terms of these 2 parameters, rho is just r e to the I phi. So this is the meaning of this variable rho. And because of this definition, in Euclidean space, we have that absolute value of rho is always less than 1, unless the 4 points lie on a circle or on a line. So for all other configurations, rho is less than 1 in absolute value. And so this rho variable is the best variable to expand the 4-point function. That's the main message. And in fact, from the UP axioms, it can be shown that the following series expansion exists. So I can take this function GUV and I can expand it as a series, as an infinite series. And in terms of the series, they all have the form rho to the to some power hi real power and rho bar to some power hi bar, where h and h bar are some positive non-negative real numbers. Their difference is an integer, and c's are non-negative real numbers. The coefficients are negative real numbers. Now I can roughly explain where these numbers come from. So these h's and h bars, they're related to the dimension and spin of the operators occurring in the OPE phi times phi. So in fact, h plus h bar is the dimension and h minus h bar is a spin. That's why it has to be an integer number. And the coefficients Ci here are squares of the OPE coefficients. Squares because I have to use the OPE twice. And that's why, since all OPE coefficients are real numbers, they are non-negative. And by the OPE axioms, this series converges whenever rho is less than 1 in absolute value, which means basically, except for set of measure 0 of configurations. And so now you see I have this power series for G, but U, V, rho, and rho bar are analytic functions of x's, of coordinates. So I can use this formula to analytically continue 4-point function, the 4-point function. And this analytic continuation will work as long as rho bar are less than 1 along the continuation path. In fact, away from Euclidean, rho bar is no longer a complex conjugate of rho. They're just 2 dependent complex parameters. So we use this formula, and it turns out that these variables rho and rho bar, they have precisely the properties that we need. So we have 2 key results about these parameters. So the first key result is that they always remain less than 1 in absolute value when we analytically continue to complex time. So everywhere we need. So there's just basically nothing else to be done. And the second property also is very important. It says that as you approach the Lorentzian, as you approach the Minkowski space, so this differences epsilon I minus epsilon j, they become zero. They become very small. So at this point, rho and rho bar may become very close to 1 in absolute value, but they do so not faster than some power of this distance epsilon I minus epsilon j and the overall size of our configuration. So there is some finite power n such that rho bar does not get too close to 1. And so using this second property combined with what we know about the Euclidean 4-point functions in conformal field theory, we can derive the parallel bound on the analytic continuation that we construct. And from the parallel bound, we derive temperedness of Wightman functions and all Wightman axioms. So it's just basically what the doctor ordered. So, okay, this may kind of come out of the blue, but I will present even more weird result about this variables rho and rho bar, just to show you that we understand a few things, but not everything. Actually, these rho and rho bar variables, so the way I introduced them to you, it was kind of completely geometric, take 4 points, compute these functions, evaluate these functions, you get 2 numbers. Now, I claim that these variables rho and rho bar, they satisfy a certain Cauchy-Schwarz-like inequality. So in fact, the maximal value of rho and rho bar in absolute value is less than or equal than the square root of the maximal value of rho 1 bar times the maximal value rho 2 bar, where this rho 1 bar, rho 2 bar, they are computed for 2 different configurations. So my initial configuration of points, it had 4 points, x1, x2, x3, x4. Now I'm going to form 2 configurations. I'll take x1, x2, and then I'll reflect them, x2 theta, x1 theta. And analogously, I will construct such a reflection symmetric configuration out of x3, x4. And since now my times are complex, I have to generalize my reflection operation. So when I act with theta on a complex time, I only reflect the real part, minus epsilon plus it, but not the imaginary part. And so the claim is that this rho bar satisfies this Cauchy-Schwarz inequality.
Oh, excuse me, just to be clear, this is in arbitrary dimension?
Yes, this is an arbitrary dimension.
Thank you.
Now, the really weird thing about this inequality is that it's a completely it's geometric inequality. And you would think that it should have some simple geometric proof. Maybe you should try to move points around using conformal transformations and things like that. But no, the only way we know how to prove this inequality is to appeal to some non-trivial properties of special conformally invariant functions, which are known as conformal blocks. So it's a pretty indirect argument, and yeah, I'm really puzzled about this. So I was just wondering, and given that this is a very unusual audience for me, maybe somebody just knows this sort of inequalities, and then I'd be really happy to hear more about it. But actually, we don't need this inequality as such, but so it's a very neat inequality, and using this inequality, which we can prove, we can show this, that the first 2 properties, 1 plus 2, they hold with optimal power n. But we can also show one and two without using this inequality, this independent proof, which, however, doesn't look as natural as using this inequality. And so this basically brings me to the end of my talk. So I can now compare the two constructions. So I reviewed the Glaser-Osterwalder-Schrader construction, which has an advantage that it works for any quantum field theory, but it has some also kind of unusual and not very convenient features, that it involves all endpoint functions at once. So if, for example, if I just want to consider 4-point function and continue 4-point function, I cannot do this in that framework. And also I need this growth conditional correlators with the number of points to show temperedness. And this also, although it may be unavoidable, but I would love to understand this condition better. I know it has some meaning if you think in terms of random measures and such, but I would like to understand it still better, this condition. So in our work instead, so the disadvantage is that we are limiting our attention only to conformal field theories, but we do have this plus that our construction works for one correlator at a time. And also, even though so far we have only done it for 4-point functions, I think it's an open problem, but I'm pretty sure that by finding an appropriate generalization of these raw variables, which are called radial conformal variables in our field, probably it can be generalized also to higher point functions. And so just to finish, I wanted to mention one further direction that I'm sure many of you have seen this famous picture, which I have taken from a famous paper by Lusher and Mack. So in that paper, they were arguing that correlation functions of conformal field theories actually can be analytically continued not just to the Minkowski space, but a much larger space, which they called Lorentzian cylinder. So Lorentzian cylinder, it's a manifold with Lorentzian metric into which the Minkowski space can be conformally embedded. So there's this dashed region here is the conformal embedding of the Minkowski space into the Lorentzian cylinder. And also in modern theoretical physics, this is what people call the boundary of ADS space, this Lorentzian cylinder. And the conformally embedded Minkowski space they call Poincaré patch. And so they wanted to prove that I mean they had this conjecture that correlation functions can be analytically continued to the Lorentzian cylinder, but they didn't quite prove it, because what they did is that they carried out the Glaser-Osterwalder-Schrader construction to go all the way, almost like all the way to the Lorentzian cylinder, but they didn't have the temperedness estimate, and they couldn't go all the way, and they couldn't show that the correlation functions on the cylinder are tempered distributions. So this is, in the conclusions of that paper, this is left out as an open problem for the future. And as far as I know, this problem has never been solved with whatever assumptions. But using our construction, using this raw variable construction, we can, at least for the 4-point functions, we can do this until the end. So we can show that indeed correlation functions do extend to the full Lorentzian cylinder. And as I said, hopefully also for higher point functions, this will be also done using this approach in the future. Thank you very much.
Hi, Slava. This is Stefan speaking.
Hi, Stefan.
I wanted one thing that people often assume is a stress tensor. That didn't seem to play a role in your construction, obviously, but does that have a natural place?
The stress tensor, it doesn't play. So the stress tensor didn't play any role in our construction. In general, it's an interesting question, like what is the precise role of the stress tensor in conformal field theory? So the big role of the stress tensor in conformal field theory is to construct charges which are your symmetry generators, space-time symmetry generators, by integrating the stress tensor against some conformal conserved Killing vector fields. And you can do it in 2 dimensions, you can do it in high dimensions, so the logic is exactly the same. But once you constructed those charges, okay, you may forget about the stress tensor in a sense. So, and in this Euclidean CFT axioms, the way I presented them, I assumed that my correlation functions are conformally invariant, and I assumed that all my fields form multiplets on the conformal group where there's a primary and the descendants and so on.
But for example, if you take a generalized free field, which with the appropriate Lehmann weight, this is a standard example where you do not have a stress tensor.
Yeah, you do not have a stress tensor, and that example it will satisfy the Euclidean CFT axioms.
Yeah. But there's something there's something from other viewpoints essentially different in this model than sort of from the usual models with the stress tensor. So is there any other way in which the stress tensor helps other than these global transformation laws, which I think the stress tensor is more than having not just those?
No, I mean, definitely. So from my point of view, there are this is a very interesting discussion. It's a bit open-ended, but it's very interesting. So there are some conformal field theories which arise as endpoints of renormalization group flows starting in the UV from Gaussian theories, from local Gaussian theories. All those conformal field theories will have a stress tensor. And so if you know in advance that you are trying to corner a CFT which arises in this way, then you can impose the assumption that your CFT has a stress tensor. If you pose this as an additional assumption on top of the Euclidean CFT axioms, so I kind of presented the very minimalistic version of the axioms, but you can impose the existence of the stress tensor as an extra assumption. If you impose this as an extra assumption, then it will allow you to rule out a big chunk of theories and focus on the local, what we call local conformal field theories. But this word local, it's kind of, it's a circular, because we call conformal field theory local if it has a local conserved stress tensor operator. But for this analytic continuation story, it really, you are right. It doesn't really play much of a role.
I mean, could you? I mean, the question is that if you have some word identities, would those help in further constraining this in a useful way or not? For example,
they do, yeah. For example, there were some bootstrap studies of the 4-point function of the stress tensor operator in 3-dimensional conformal field theories, and in those studies, they posed also word identities, because word identities, they constrain 3-point functions of the stress tensor. Yeah, so if you assume the stress tensor, you go all the way. You like assume all the word identities and everything else.
Mm-hmm. Okay.
Slava, what is the meaning of this n capital that you have several times? Does it have a physical meaning, or what one should think about it?
You mean this n capital, I guess.
N capital, this one, yes, yes.
Yeah. So mathematically, I said that this number will control the regularity of your distribution. So how many derivatives you need to have for the test function for distribution to be integrable against it. The physical meaning of this number, I'm not sure. If this number is it's a good question. I should think.
Does it depend?
I should have a slick answer to it, but I don't.
Does it depend on the theory that you consider, the particular feature of conformal field theory that you? So it depends on the theory that you consider, right?
Not in this lemma. So this n here does not depend on the theory, because this is just this only depends perhaps on the number of dimensions, but not on the theory. Because here I'm just talking about rho and rho bar, which is just some geometric variables which depend on the 4-point function configuration. But later on, I will use this n in the bound on rho in order to derive the parallel bound on the analytically continued 4-point function. And that number will depend on the theory, because it will depend on it will depend on the scaling dimension of the fields that I'm considering. Yeah, but I'm sorry, I don't have anything more intelligent to say.
Slava, I wanted to ask about this, your bootstrap, your OP axiom. So are there any constraints? So what the spectrum is? What are the dimensions of fields which you have there? I mean, you said that it you just assume that it converges, right?
There are constraints. So what are the constraints here? So first of all fields appearing in the OP have to be fields which are allowed to exist in the theory by unitarity bounds. So for example, scalar fields, they will have to have dimension larger than d over 2 minus 1. If I take fields of higher spin, they will have to have higher dimension and so on.
But otherwise they can be arbitrary, right?
Otherwise they can be arbitrary, and okay, I did not say this explicitly, but we usually like to assume that in at least in dimension d larger than or equal to 3, the spectrum of the theory is discrete, which means that scaling dimensions of fields, they do not have any accumulation points at finite values.
Mm-hmm.
This is not a crucial assumption. Like, for example, conformal bootstrap results do not depend on it. But all known examples seem to in higher dimensions, they seem to be of this kind. So in 2 dimensions, we have some CFTs which have continuous spectrum, but in higher dimensions, this doesn't seem to occur. So the number of fields appearing in the OP can be huge. So first of all, it's always infinite in higher dimensions.
Mhm.
And it can be really huge. There's an exponentially high number of fields appearing, and by now there are some pretty interesting analytic understanding of how to think of various families of fields, so they can be grouped in some families. There is an interesting theory of Regge trajectories, which allows you to group fields in some families, which I clearly did not discuss at all. But then there are some other fields which don't seem to belong to any Regge trajectory, which we seem to see numerically. So the current understanding is that there is just gazillion fields out there, and most of them have very tiny OP coefficients. And so their presence does not invalidate convergence of the OPE.
So also the structure constants, they can grow like crazy.
No, the structure constants cannot grow like crazy, because if they were to grow, then combined with the number of fields, the OP would diverge, because there are some configurations. There are some configurations of points where you can see that all terms in the OP contribute with the positive sign. So if structure constants were to grow, then at least at those points, OP would diverge. And so if we assume that it converges, then a posteriori we conclude
right.
that.
So this is an implicit assumption about Fs also.
Yeah. This is an assumption about, so Fs have to be, if there are many fields, if there are too many fields, then Fs have to compensate for this becoming very small.
Yeah.
So this is well, this is an axiom. I don't know. It has not been proven. From some other framework.
Well, thanks.
I see some raised hands. I don't know who was first. I mean, in my list, Yo Tanimoto is on top. Yo.
Hello. I wanted to ask, probably I missed something simple, but on how is locality encoded in the OPE axiom, or does locality play any role in your work? A locality in the sense that if you exchange 2 variables and the correlation functions stay the same.
Okay, thank you. It's it's a crucial question. So, locality, actually, I did not state it explicitly. I'm sorry, I forgot to write it. So it is in fact locality in the sense that you say. It is one of the axioms. So
well, I see. So you assume it.
It is assumed as one of the axioms because it's physically meaningful.
Yes.
And then but you are totally right. The OPE is not manifestly consistent with locality.
Yeah. So I wondered
how. And so the whole constraining power of these axioms comes from this fact. So you know that the correlation function has to be expandable on OPE, and also you know it has to be local, has to be permutation invariant. It turns out that if you put these 2 things together, then the parameters of the theory, these deltas and Fs, they have to take pretty special values, otherwise these 2 properties are not consistent.
I see. Okay. Thank you.
There's a further raised hand, Abdel Malik Abdesalam.
I think Michael wanted to ask a question before, but
okay.
But anyway, so I was wondering, because the growth condition in Osterwalder-Schrader is extremely forgiving, because you allowed any power of n factorial like to the 20 million. And what goes wrong if you just iterate the OPE, you have your fusion tree, and you have some kind of naive bound, maybe on the F, the OPE coefficients? Why can't you beat n factorial to the million?
To tell you the truth, I haven't tried very hard. But when I thought about it, it seemed to me that it was really inaccessible, because there was just there is just too little because okay, so if we start considering higher point functions and expand them using the OPE, we will encounter some sums of OPE coefficients where those sums, they will run over multiple indices of this OPE coefficient. So it's going to be like double sums or triple sums and so on of multiple products of OPE coefficients. So somehow, so for example, from the fact that the 4-point function is finite, I can derive some constraints on the spectral density of my fields weighted by OPE coefficient squared. But only when I vary one index of the OPE coefficient. For example, the two indices stay low. For example, 1 and 2 stays low, but the index k can become large. And I know something about how the density behaves in the k going to infinity limit. Because if it grows too fast, then the correlation function will become infinite. But if I start studying this higher point functions, then I will somehow have to take into account the OPE coefficients where several of these indices, I, j, k, all of them can become large. And perhaps something can be done about it, but this looks, to me, it looked daunting. So perhaps I was too pessimistic, and it can actually be done. So it'll be interesting to think about this carefully, but I don't know of any results in this direction. Yeah.
Okay, I saw that there's a question via the chat. Can you read it, or should I read it?
Yeah, so Michael Eisenman is asking if there is some simple example of unexpected Euclidean relation which is implied by Lorentzian axioms. I can in this context of the average null energy condition, I can definitely say something. So let me go to that page where this ANEC was discussed here. So this, I'm not sure it's going to be your favorite observable, Michael, but this 3-point function of stress tensors in any conformal field theory, it depends on it actually has only three conformally invariant tensor structures in any number of dimensions. So you can, so there are 3 functions, let me call them F1, F2, and F3. And there are 3 numbers, C, A, and E. There are 3 they're called C, A, and E. These are three proportionality coefficients. So in any conformal field theory, this three-point function is proportional to this linear combination, equal to this linear combination. Now C turns out to be the same number as which enters in the two-point function of the stress tensor itself. So in 2 dimensions, it would be the central charge of the theory, but in higher dimensions, you can introduce this parameter, but it doesn't have the same deep meaning as in 2 dimensions. And so it turns out that this average null energy condition, it allows you to put bounds on the ratio A over C. So it can tell you that A over C is less than some upper bound and lower bound in any theory. And this upper and lower bound, it's saturated by less than or equal by free theories. So it's kind of interesting that condition is satisfied for any theory which is not free. And so when people studied, my colleagues studied the bootstrap constraints on the correlation function of 4 stress tensors in 3 dimensions, they could, for example, see that the 3-dimensional Ising model, so it was a purely Euclidean analysis, so they did not use at all Lorentzian physics, but they could see, for example, that the 3-dimensional Ising model satisfies these constraints following from Lorentzian average null energy condition.
I see. I mean, there are things like, for example, in the class of inequalities which are saturated by Gaussians and varied more generally, like the ratio of the truncated 4-point function to the full point function, which is related to the renormalized coupling constant.
Yeah,
it's of definite sign and bounded by 2 in modulus. And I wonder if there's anything of this nature which was hidden from us. So that I should look at that. But thank you. It's a beautiful lecture. Thank you very much.
But there are I mean, this is just one example, but there are really tons of examples. Now nowadays people now Lorentzian is the new black. Everything now is done Lorentzian. If you look at the literature, people have discovered so many beautiful things there. And the question is, does it really apply to the Ising model, or does it require extra constraints?
I see.
The bet is that it does apply to the Ising model.
Thank you. Beautiful lecture. Thank you.
Okay, I see no further questions. Stefan?
I just ask a general question. It's Tom Spencer. So if these problems really arise from the massless nature of the theory? I mean, if I had a massive scaling limit, then would all these problems disappear?
Which problems? Problems of,
well, for example, just constructing the Wightman axioms.
Well, no, they would become more complicated because for massive theories, we do not have currently a well-understood OPE framework. So OPE only works for conformal field theories. It works, and we conjecture that it should be. But for massive theories, there is no good OPE framework. So, yes. So for massive theories, there's currently no alternative to the classic Osterwalder-Schrader construction.
So if I want to do a massive scaling theory for, I don't know, 543 with a mass, so I have a well-defined theory, then I still cannot recover Osterwalder-Schrader. I think it has to do with the scaling limit that you're doing somehow, right? Otherwise, I don't imagine there's a problem. I'm just trying to understand the origins of the difficulty here.
No, but you see, the way people, there is some truth to what you're saying, but it's only partially true, because when people do, when people construct phi to the fourth, they nowadays they realize it as some sort of random measure, and when they realize it as a random measure, they get automatically kind of it's a part of the construction. They get some bounds on the moments of this random measure, and those bounds they imply this linear growth condition, which is needed in Osterwalder-Schrader framework to recover Wightman. So in that framework, they do recover Wightman.
Okay, okay. Yeah, that's what I thought.
But they only recover Wightman axioms for the correlation functions of phi. Now, there are many other fields in this theory. Phi squared, phi cubed, phi to the fourth, stress tensor, you name it.
Yes.
Those fields are not obviously random distributions.
Okay.
We do think that they have well-defined Euclidean correlation functions, and we do think that that correlation functions of those fields also satisfy Osterwalder-Schrader axioms.
Yes, I would have thought so.
Yeah. But since those fields are not random distributions, I'm not sure it's easy to argue that that the growth condition remains true also for them.
Okay.
And so we don't know. So we have this weird situation. We know that the correlation functions of phi satisfy Wightman axioms, but for correlation functions of stress tensor, nobody discusses if those satisfy Wightman axioms. I haven't seen this. Maybe somebody does, but I haven't seen this.
Yeah. I see. Okay. Yes, I understand what you're saying. Actually, I think there are some people who have been thinking about such questions, not so much for 3 dimensions, but for 2.
Right. I think maybe one last question. Otherwise, maybe I have the last question. In perturbation theory, one also, of course, doesn't have Osterwalder-Schrader positivity because they're just formal series, and positivity is trivial requirement. So there also one needs a sort of more explicit analytic calculation, order by order, where sometimes some Mellin-Barnes type representations are very, very useful because they cover different configurations of points. Is that a useful tool also here? I mean, is there like a Mellin-Barnes representation of a 4-point function? Because that's very convenient for analytic continuation.
Yeah, Stefan, you are right. Indeed, this Mellin-Barnes idea has been used in some explicit calculations. For example, for n equal 4 super Young-Mills, people computed 4-point functions in Euclidean, and they wanted to study some of these Lorentzian observables having to do with the average null energy condition. So, and so they needed to continue this correlation function from Euclidean to Lorentzian, and the way they did this, so this is the work of Grisha Korchemsky, Sasha Zhiboyedov, and Emery Sokochev, and probably somebody else. And the way they did this is indeed, like you're saying, they took the perturbative theory result and they express it as a Mellin-Barnes integral, and then what you have under the Mellin-Barnes integral is just a rational function of the distances to some power, so you can analytically continue that. And so that was a nice prescription. So it's at least for computing, because I'm not sure it can be made into a rigorous proof of Wightman axioms. So this because you would have to deal with convergence of these Mellin-Bar integrals. There's actually some pretty interesting work of Mellin. I mean, there's a lot of work on Mellin representation also for CFTs. Actually, Mark himself discussed this in one of his last papers so far, and people are still pursuing it. So perhaps this is going to give some other way to construct Lorentzian physics. Yeah. So.
Thank you for answering this last question. And with that, I think we're well over time now. And thanks to you again for giving this beautiful lecture, and to the others for asking many questions.
Thanks. It was a pleasure.
See you around next month.